Real? You want to talk about reality? Dig pretty deep, kiddo, before you can find anything real. We live in a kingdom of bullshit.
We are starting a brand new subject today. It's one, though, that is integral with the course, and that's the study of the oceans. As we'll see, not only do the atmosphere and the ocean interact, each influences the other, which makes it necessary to understand both, but also to some extent they obey similar laws of physics. For example, questions of static stability. When will a column of air turn over? When will a column of water turn over? Learn a few new things about the ocean, but to establish more linkages between the things you've learned before and the things you're learning now.
Let's go ahead and take a look at some of the flattest parts of the features. Now, people get this confused a lot. Number 5 right here, and number 5 right here, and number 5 right here are all the same thing. Those three number 5s are all abyssal, Y-S-S-A-L, plains, P-L-A-I-N-S. An abyssal plain, and like we talked about in class, abyssal plains are the flattest parts of the ocean. They're essentially featureless. They're not the deepest parts of the ocean, but they really have nothing going on. It's hard for life to really exist down there in great abundance because it's so deep within the ocean. Sunlight doesn't get down there very well, but there is still life down there. But the main point here is that these are really the flattest parts of the ocean.
There's a section of abyssal plain, a kind of flat-lying section. Flat in part because it's composed of sediments that have fallen from above. And as they fall, they fill in the cracks first, and then they, as you get quite a pile of sediments, it tends to give you a flat surface. A mid-ocean ridge, one of these spreading centers, where magmas are coming up and forming new ocean crust, tends to be elevated because those rocks are still hot and less dense, and they float a bit higher than cold ocean crust until they cool down, and then they sink a little bit away from the spreading center. But that could come up a bit. If this abyssal plain is at 5 kilometers, then these mid-ocean ridge might only be 2 or 3 kilometers below the ocean surface. So now here's the whole world ocean, and the color scheme is not quantified on here, but I can tell you basically what's going on. All the deep blue is abyssal plain, about 5 kilometers deep. And you see it a lot of places. These little lines that run up through the middle of oceans, for example, in the South Pacific and in all the way up through the Atlantic, the South and the North Atlantic, those are spreading centers, mid-ocean ridges. And then the trenches don't show up well on this diagram, but they are the darker blues still. And you see a little thin line along there that's a trench. You see one here. You see an important one here and up along here, and even along the tip of the Aleutian Islands. So those are the subduction zones.
The ocean floor is actually being pushed down, and as it goes down, it leaves a deep, deep canyon in the ocean floor. We call it a deep sea trench. A deep sea trench is actually the deepest part of the ocean anywhere. In fact, the deepest hole on Earth is the Marianas Trench, and the Marianas Trench is over 36,000 feet deep, and it's the deepest place on the planet.
One of the strangest places on the ocean's floor was only just discovered in the 1990s. And Mike Degree is one of a handful of people to ever see it in person.
Without a doubt, one of the most amazing things that I had ever seen in the bottom of the ocean, and it was while filming for Blue Planet, was in the Gulf of Mexico. And I noticed there's something out in the distance, couldn't tell exactly what, but it looked like a dark band. And as we approached it, the dark band became a donut. I saw this donut that was black in the center. What the heck is that? And so as we get closer and closer to it, I noticed that the black band had what appeared to be kind of steam over it. And then I looked, and there was water lapping against the shoreline. This band was a ring of mussels. And inside the ring of mussels was a lake. And it's like, wait a minute, I'm already underwater. We went out over the water in this lake and tried to descend in it and bounced off. It was so super saline and dense that the submarine couldn't go down in it. We literally bounced off, and as we bounced off, we sent ripples heading back to the shoreline. It was insane. I've never seen anything like it.
The density of seawater is controlled primarily by the temperature and the salinity. The density is a very important quantity, but if you know temperature and you know salinity, you can compute or you can measure the density. So what's plotted in this final panel is the density derived from the measured temperature and salinity. And it shows a lower density water near the surface. By the way, the units are in grams per cubic centimeter here. Remember, fresh water has a density of about 1 in those units. So this is a little bit denser than fresh water and gets even denser by the time you get down to the bottom, primarily because of the temperature in this case. The colder temperature is giving rise to the lower, to the higher density in the deep ocean. The point I want to make here is that there are 2 types of crust. Continental crust is generally of a lighter material and floats a bit higher in the semi-molten parts of the mantle, whereas the ocean crust is a little bit denser and floats a bit lower. So you've got basically a lower floating ocean crust here and a less dense, higher floating continental crust. Well, they're made of slightly different chemical compositions. Normally, there's more, I think, more quartz generally in these rocks that as a light mineral allows it to be a little bit denser, a little bit less dense, and other denser minerals are found more prolifically in the ocean crust, which makes it a little bit denser. Okay, we'll come back to that. But I wanted to make this point. So when you then take a, what's called, make a hypsometric curve, and I'm going to focus on the bar graph over here on the left. This is elevation in meters above and below sea level. Sea level is marked at 0 here, which I remind you is a somewhat arbitrary choice. It depends on how much water we have in the oceans. And over geologic time, that has probably changed a little bit. For example, when you have an ice age, you store some of that water up on the continents in the form of glaciers, and sea level drops a little bit. So that is kind of an arbitrary reference point, but it's commonly used, and so we'll use it here. What's shown in the bar graph then is the percent of the Earth's surface that lies, for example, between sea level and 1 kilometer above, and it's about 20% of the Earth's surface. Between 1 kilometer and 2 kilometers above sea level, it's about 5% of the Earth's surface. And you find some parts on the continents that are even higher, even up to 4. But you know, in fact, Mount Everest is up here somewhere. There's even a little bit of land that lies 9,000 meters above sea level. Going down below sea level, you find there's not much land at 1 kilometer, 2 kilometer, and 3 kilometers below sea level, but a lot at 4, 5, and 6 kilometers now below sea level. Now this is a bit of a surprise, because if the Earth was just a rough surface, had been roughened by some process, it would have kind of a normal distribution for this hypsometric curve. It would have some average height and then less above and less below. But actually, no, this has a double peak, a very interesting double peak. And of course, that has to do with the point I already made. There are 2 types of crust here. This is continental crust and this is ocean crust. So this plate tectonics that gives us the 2 types of crust, ocean crust and continental crust, is the cause for this double peak in the hypsometric curve for land elevation. And again, it just so happens that we have an amount of water that puts most of this down below sea level, and some or most of the continents just at sea level or slightly above. The way we know all of this, by the way, is from acoustic depth profiling. So you take a ship and it sends out an acoustic signal, a sound wave, and you bounce it off the bottom and you time how long it takes for that signal to go down to the bottom of the ocean and then back up again. And in the old days, you just had a single pinger going right directly down, so you'd have to take the ship back and forth on a very complicated long route to map out the ocean. But now they can set it out in a fan with different acoustic beams going in different directions, so you can do a single swath as you go along and get depth over some range to your left and to your right as the ship sails along. And the thing that's going to be very important to us is the way that these continents tend to break up the oceans into segments. For example, Asia, with Australia included, and North and South America break up the Pacific Ocean into kind of a north-south oriented ocean. North America, South America, compared with Europe and Africa, break up the Atlantic again into a north-south oriented ocean. The Indian Ocean is a little bit different because Asia fills the northern hemisphere, most of it, down to about, say, 20 degrees north latitude. So the Indian Ocean is primarily an ocean just in the southern hemisphere. And then the one gigantic exception to this is the so-called Southern Ocean. The term for that strip of ocean that goes all the way around the globe, it's usually called the Southern Ocean in oceanography. And if you go far enough south in the Pacific, you join onto it. The Atlantic, you join onto it. The Indian, you join onto it. And as we'll see, you can have ocean currents here that go right around the globe. Whereas at all these higher latitudes, any ocean current that moves east-west is going to hit a continent and is going to have to wrap back around. So you get what are called gyres in most of the oceans because they're confined by these north-south oriented barriers. So gyres are the things we'll be studying for most of the oceans, but not in the Southern Ocean. There we'll be able to look at a current that goes all the way around the globe. Questions on this?
We have deep sea trench. We have abyssal plains over here and over here. Flattest places on Earth. Flattest places on Earth.